Cool. And then we have questions before we start. You want to see me cook? Okay. All right. Yeah, yeah, sure, yeah. I don't know if we're gonna have enough time to go through all of it, but yeah, we can certainly try. Yeah. Um, okay, cool. We'll start on number one. All right. Uh, if you want to just go through the whole thing, feel free. So you guys should have this on your Canvas page, but go ahead and go through the whole thing. And I'll give you guys like 5 minutes. It's okay if you don't finish all of it. And I'll probably fill it out as we go, honestly. What? Okay. When you're done, feel free to look at what I've done here. But if not, don't worry. You guys still have like two something minutes, so you might have made a mistake as well. So if I made a mistake, just yell at me because I try and do this kind of quickly, but because I want to leave time for you guys to ask questions if you have questions. Good. Right. So it's asking how many side chains, right? How many side chains in here are actually basic or acidic? Yeah. Yeah. Yeah, yeah. Make sure you read it, huh? Lysine, right? Where's lysine? What number is it? Second to last, right? Good. Yeah, yeah, good. Yeah. So lysine is the only one that's basic there, right? The thing that everybody makes a mistake on is not reading the question properly, right? And then they say, "Oh yeah, well this is charged and this is charged, right?" Well, you're right, they are charged, but the question is not asking for that. Yeah. So what were you saying? Sorry. Glutamine's not charged, right? Glutamine has no pKa, right? What's the pKa of lysine? The pKa of lysine? What? We had to memorize them. Yeah. Yeah. Even if you don't have to memorize them, I still think that knowing generally where they are makes the exam faster. pK of lysine is about 10.7. Right. Uh-huh. Yeah, so 10.7 is around lysine, right? It's around 11-ish, right? Arginine's around 12. I would say you don't have to memorize them if you don't need to, but I'm telling you right now that if you memorize the pKa's, there's only four of them, right? Or maybe five or six, right? But if you memorize them, the amount of time you take trying to look at back at the sheet and everything. You don't have time for that, right? Memorize as much as you can, right? It makes things faster, right? Right. Okay, cool. So we all understand. Do we understand what's going on here? Does all this make sense? Any questions about any of this? Yeah, so I don't know if you guys have covered this yet. I don't know if you will cover it actually, but when we took this class, aromatic rings, right, have the ability to absorb high energy, right, or like wavelengths, low wavelengths of high energy, right. So you aromatic rings like tyrosine and tryptophan are the two ones that are the main ones. Phenylalanine is weird for some reason; it doesn't actually absorb it very well because there's not a lot of resonance. So yeah, shut up. There's not a lot of resonance, right? So that's why phenylalanine is not the best answer here. Tyrosine and tryptophan are the two options that you would pick if you ever get a question about absorbance of light. Hmm. There's no tryptophan, right? Yeah, there's no tryptophan, right? The tryptophan is like really obvious to spot, right? Tryptophan is like massive, right? Um, right, yep, right, good, right, right, yep, right. It's asking position, right? So make sure that we're reading the question carefully, right? But and then everybody understands this phi psi angle BS, right? Yeah. I just remember that the N to C bond is the phi angle, and the C to C bond is the psi angle, right? So this right here is psi, right? This would be phi, right? Good. Any questions about this page? Yeah, I always the way I remembered it was fine. So PHIN, and then the only one that has N is the N to C bond. So it's a bit of a weird way of remembering it, but that's just how it worked for me. Just the word fine, right? But it's spelled differently. So whatever works for you, right? It doesn't have to be how I remembered it, but that's how I remembered it. A little mnemonics are helpful. They shouldn't test you on this weird turning nonsense, right? Where they do all the like alpha helix stuff and beta sheet stuff. What's the spy sine angle of those? They have other things to test you on, right? They could, but it's not very likely. Any other questions about this page? The what? I think there was a chart. The Ramachandran chart was on your thing, but they didn't really go in depth on it, right? So, huh? Yes. Yeah. Any other questions about this? Nope. Okay. Good. We're moving on then. Okay. Now you get to have fun. So I'll give you guys a little bit of time to look at this, and then we'll move on. I'll say probably like I'll give you another 5, right? Welcome in. We all good? Yeah, you guys finished that with 1 minute left to spare, so good, right? Okay, so does this all make sense? Right? Okay, so I mean, like, I guess I'll go over it very briefly, right? So all that we're doing, right, is we're looking at these different pKa's, right? The 9.6, the 4.3, right? And we're trying to figure out which of these structures corresponds to which pK, right? If you use a number line method, this goes by really quickly, right? So remember, right, we have our number line, right? The pKa of the first one is 2.2. The second one is 4.3. And the last one is 9.6. Apologies for my writing, I can't draw on this thing. But we know, right, that we're looking at, this looks like glutamate, right? And we know that if we drop all the way down to pH 0, right, we're going to be positively charged, right? All the groups that we have are the COO group, right, the COO group, and this H2 group, right? At pH of 0, the amine will be protonated, the carboxylate will be protonated, and the carboxylate will be protonated, right? So we'll have a +1 charge down here, right? That's below pKa, this pKa, right? Which one of these has a +1 charge and only a +1 charge? That's just C, right? The other options you have that have a plus charge on the amine are B and D, but they have a minus charge here and 2 minus charges here, right? So it cannot be B and D, right? It has to be C. Good so far? Okay. If we move on to the next one, right? For B, right, we're going to move up here. This has to be 0, right? Just by how this logic works, right? This has to be -1, this has to be -2. I'll fill all those out, right? This makes sense so far, right? How this number line technique came up, like how we're using it to solve for this, right? Okay. Which one of these has a 0 charge, right? We've already used C, so it can't be C, right? The only one here that has a charge of 0 on it is B, right? It's not that all the atoms are neutral, it's just that the addition of the charges adds up to be 0, right? So this plus and this minus cancel out, right? Therefore it's 0, so it has to be B in this second option here, right? So you can eliminate that. Now, moving on to the back end now is where this can be a little bit confusing because now you have two pKa's, right? That can make this negative, right? So the first thing we have is the 4.3, right? If we put our pH at like 5.6 or something, right? We're going to be in this range right here, right? We're going to be at this -1 charge, right? We have to look for which ones have a -1 charge. This has a -1 charge, right? So we can circle that as an option. This is -2, it can't be D, right? And this is also -2, so it can't be that. Oh, sorry, wait a minute. Sorry. This is, yeah, it can be D, because there's a plus here, minus here, and a minus here, right? So it can be D, right? So, can be D, right? It cannot be A, because A has 2 negative charges, right? So we can get rid of A, right? Now it's between D and E, right, for our answer, right? And now we have to think about the pKa's of the individual groups that we're at, right? So, if we are at, let's say, pH 5.6, or let's just say pH 6 to make it simple, right? The amine, right, is basic. It'll be protonated, right? So the amine has to have a positive charge. Immediately, you can actually go ahead and eliminate now because E doesn't make sense here, right? Because E doesn't have a positive charge on the amine. But for the sake of continuity, we'll go through the rest of it, right? So the amine has a positive charge here. That's great, right? This doesn't, it's a bit, right? If we go to the next group, the pKa of this side group here is about 4.6-ish, right? And the pKa of this is about 2 or something, 2 or 3, right? So if we are at pH 5.6, right, this will be deprotonated, right, and this will also be deprotonated, right? So those will both be negative. Furthermore, this is also incorrect because of this, right? That has to be deprotonated, right? Because the pK of that is like 4 point something, right? So by that logic, we can say that it has to be D, right? So we can eliminate that and put that here. The last one just has to be -2 charge, and there's no other option here that's -2 charge, right? If you want to think about how this works, right? If you go above pH 9.6, pH 11, right? Let's say, right? The amine is the amine would be neutral, right? Because we're not below its pKa, right? And the two carboxylates would be deprotonated because we're above their pKas, right? So those would be deprotonated. Those would both be negative. The amine is neutral, and it's going to be -2 charge. Good? Right? There's no other option here that has a -2 charge on it, right? So it's going to be A, right? That makes sense, right? We're all good there, right? For this is a funny question that probably trips up a lot of people when they first see it if they don't understand how PI works, right? The PI by definition is the point at which the charge is zero, right? So without doing any sort of math or anything, right, you must say that the net charge is zero, right? If you want to do the math, go back up to the number line, right? We look at what the PI is, right? The PI is the point at which the net charge is zero. Therefore, it must be zero here. Also, if you think about it just logically, right? If the pH matches the pKa, right? There's no difference between those two, right? So the charge has to be zero, right? The predominant structure, right? Which one is a zwitterion, right? Which one has a charge of zero? B, right? It can't be any of the other options because none of them have a charge of zero, right? B is the only one, right? So those should be relatively safe, right? Relatively easy. I would say for those are the ones that you can probably like do first. Get your brain going, right? Because some of the ones at the bottom are kind of devious. But yeah, this is still going. Okay. So this is where you have to do some math, right? But the math shouldn't be too bad. This first one here, you just have to make the equation, right? You don't have to do any math for it, right? Now, you might be wondering, how did I pick the pKa, right? Just pick the one closest to it, right? You could theoretically pick the 2.2 and the 4.3 or the 4.3, but good luck adding enough base to get up to the next to get up to the next one, right? So pick the one that's closest to it, right? Also, just notice how nice the numbers are. They will make the numbers chill, right? Notice how 9.6 to 8.6 is a decrease of 1. Very nice numbers, right? They've made that very easy for me, right? So just for the equation, right, we say pH is equal to pKa plus the log of the base over the acid, right? Since we are using this pKa, right, we are up here, right? We're in that range, right? The base is A, and the acid version is D, right? Any questions on that? Huh. Yeah. Yeah, you're supposed to use PK2. You're right. I actually would have lost points there. Good catch. Yeah. So yeah, you use PK2 there. So use PK2. Don't do this. This is wrong. Use PK2. I actually did lose points on this question because of my explanation down here. They did not like. I didn't use A over D. I used base over. I wrote base over acid, and they didn't like that. Yeah, this is my test. Yeah, yeah. So I wrote base. I wrote this. I wrote base over acid, right, instead of A over D, and they dock points for that. I didn't do that on my exam. I actually wrote PK2 because I was smarter back then. Yeah, they would have. They would have definitely docked you if you wrote 9.6. Yeah, because the instructions specifically ask you to use PK1, PK2, PKR. They're quite stingy with the grading. Yeah, no, they do care. So please read the question. Is what I'm saying. Right. Okay. So does that format make sense though? Right. We're just using Henderson-Hasselbalch. Right. We're using the base, which is A. We're using the acid, which is D here. Right. And we're using this pK because it's closer to 8.6. Right. Cool. Okay. this is where you have to do a little bit of math, and the math isn't too bad. Um, if you don't know your logs, it might cause problems, but hopefully you have a little bit of knowledge of how logs work. But so basically, right, we set up this equation, right? We say that 8.6 is equal to 9.6 plus the log of the base, a over d, right? All we're doing here is we're subtracting 9.6 from both sides, right? Which is how I get this negative 1, right? And then all you're doing, when you take logs, right, the opposite of a log is 10 to the power, right? So to undo this log, I just raise everything to have everything as base 10, right? So 10 to the power of negative 1, 10 to the log here, this all cancels, and you're just left with what's down here, right? And if you know like how fractions work, right, anything to the power of negative something, right, is just the reciprocal, right? So 1 over 10 to the something, right? So if I just say like, if I say 100 to the power of negative 1, right, it's just 1 over 100, right? Right? And so that just comes out to a ratio of 1 over 10, right? And that's literally what they're asking for, right? So, but in this case, they're technically asking, no, so they're asking for base to weak acid. Sometimes they will ask for acid over base, and they want you to flip the ratio, right? So be careful of that, right? So this is written in base over acid, right? They will ask you for acid over base. The MCAT does that. The MCAT asks you for acid over base sometimes, right? Yeah, right. That makes sense. Good. Just be aware of that. Basically, the moral of the story is please read the question because the questions can be devious a little bit, right? So if it says base over acid, just leave it how it is. If it says acid over base, flip the ratio, right? Okay. Questions on this section here or this page in general? No. Okay. Yeah, just feel free to yell at me. By the way, if you have questions, I don't really mind. Okay. This question is fine. This question is really mean. Yeah, the bottom question is a little bit mean, all right? There are two ways of solving it. Uh, I'm a little bit smarter now, believe it or not, so I actually know a better way of solving F than when I did on the actual test, using equivalence, but uh, maybe if I have time, I'll show you both. But go ahead have you guys done this already? No? Okay, I'll give you guys time to go ahead and do it then. Yeah, take a look at it. Go ahead and do it. I'm gonna go grab my water because I'm yeah. feel like I'm like on drugs every time I do these tests. Like I know how to do them, and I keep making stupid mistakes. Uh, yeah, literally just do dimensional analysis. You absolute buffoon. Oh my god, bro, it comes back. It doesn't matter. It doesn't matter where you are. It comes back. Wait till you do M1 V1 and equals M2 V2 and Biochem 426 again. Oh god. The lab class, yeah. Yeah, yeah, this test, yeah. uh, no, I mean, the third one was pretty crazy. But there's three, yeah. Yeah, three exams, three lab reports. Yeah. Oh god. Oh my god, I can't draw, bro. Okay. I'm trying to think about if I can try and explain this in terms of the equivalence method, though, because I feel like that one's a little bit easier. But okay, I guess you can do it like that. Yeah, yeah, you can. Yeah, that works. Yeah. So, are we good? Okay. Yeah. Yes. Did you get the first part? No. Okay. 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 Yeah. Yeah. Okay. So the I guess to just real quick recap a little bit. I put the videos in my YouTube thing, but sometimes they're not great. So, but basically, right? An equivalent, right, is just uh. This is really hard to explain. An equivalent is basically just the amount of stuff in your solution, right? So if you, for example, have 50 moles of acid in your solution, an equivalent is adding 50 moles of base, right? That number is moving though. It's a moving target. So if you change it from 100 to 100 moles of acid, an equivalent is now 100 moles of base, right? Does that make sense? Basically, you're adding enough base to completely counteract the acid in your solution, right? That's all an equivalent is, right? Does that help a little bit? Right. So what is the definition of pKa? What is a pKa, right? So the pKa, right, is the point at which the base and the acid are equal, right? So if I start with 100 moles of acid, right, to get to the equivalence or the pKa, I have to add 0.5 equivalents. In that case, in that example of 100 moles, it would be 50 moles of base, right? You see how it's half of what it was before, right? Does that make sense what I'm doing there? If you're trying to completely neutralize it, yes, right? But that's what I'm trying to do, right? So if we remember what pH equals pKa, right? Plus the log of oh my god, yeah, plus log of I'm gonna write B over A, but you guys know I mean B base over acid, right? Okay, base over acid, right? Notice the y-axis here is pH, right? If I want the pH to be equal to pKa, right? So I want 2.2 to equal 2.2 plus the log plus this stuff, right? In order for that to be true, this whole term has to cancel to 0. B has to equal A. That is true, yeah. If you add a full equivalent though, so let's say I have 100 moles of acid, right? If I add up one equivalent base, do I have equal amounts of base and acid? Do I? If I add 100 moles of OH minus? Do I have equal amounts?
Is this because it's like a weak?
Yeah. That's a good way of thinking about it. You can think about it as a weak acid, yeah. So if I add 100 moles of OH minus, is that the conjugate base of HA? It's not, right? It's too strong. If I add 100 moles of OH minus, it'll turn all 100 moles of HA into A minus, right? So now you just have no acid, right? Does that make sense what I'm talking about?
Oh my gosh, like wow.
Well, okay, let's see. Why does it have to be one half of that?
Because then you still have that's still one
Half of it is not 1 molar equivalent. So 100, yes,
hundred.
yes. If I added 100 moles of OH minus, that was 1 molar equivalent for this question. But okay, if I add 50 moles of OH minus, what happens to this number here? It would, so you deprotonate 50 moles of HA, so you would have 50 moles of HA left and 50 moles of A minus. You picking up what I'm putting down here?
So where you're
Yeah?
Okay, but then how do you get to
How do I get to the next ones, right? Yeah, okay. So, but does that make sense?
so H is left, but
Correct.
what?
50 A minuses, right? So what's the conjugate base of HA? It's A minus, right?
Oh, that's exactly what you want.
Into here. Yes. Yep.
Um,
Yeah. Yep. This whole thing of like, so strong acids and strong bases, we use them as titrants, right? You can't just add hydroxide or add H plus and say that's the conjugate base, right? Or the conjugate acid. The whole point of adding these bases and strong acids is to turn some amount of whatever is inside of our solution into its conjugate. So if I start with 100 moles of acid and I add some base, right, I will turn some of the acid into its conjugate base, right? That's what these curves show you, right? So if I add half an equivalent, or in this case 50 moles of OH minus, I will end up at the pKa, the first pKa, right? Because I've just turned 50% of my solution into the conjugate base when I started at 100% acid. So if I add, for this example here, right, this example, if I start with 100 moles of acid, right, I'm at this low pH of like something like 0, right? If I add 50% of this amount, so 50 moles of hydroxide, strong base, right, I will deprotonate 50% of this acid, right? If I deprotonate 50% of the acid, right, that means 50% of this is turned into the conjugate base, right? The A minus form, right? And so now I have a 50-50 mixture of the acid HA and the base A minus, right? And because of the whole thing up here, if I just substitute those in, that's 1, log of 1 is 0, right? And you get this pH equals pKa, right? Which is what this point is showing you right here, right? Yeah? Yes. Yep.
so let me put a blend. OH deeper. Now you're looking towards the second OH, and it's the same 0.5 thing for the second OH to be deprotonated.
I think I understand what you're saying. Yeah, I think so. Yeah, if I think that makes sense. But okay, so basically, right, to go from this right, so but yeah, right. So you add 0.5, right, and you get to the pKa, right? That's the pKa. If you add another 0.5, you get to the equivalence point, right? Now you've turned all of your acid, right, into conjugate base, right? But remember, with amino acids, especially for things like this is glutamate, lysine. Lysine? What is this? The glutamate. This is glutamate, right? So for glutamate, right, there are 3 pKa's, right? So once you get past the first pKa, you have to do the same thing for the second one and the third one, right? So when you add when you add one equivalent of base, right, you now get to the point where you're at the next pKa, right? So we've just overcome this 2.2 pKa, right?
Why is the pH increasing a lot for the equivalent for one PKR?
Between pKa1 and pKar.
Like
Yeah.
PK2, well, like increasing pH and this one there.
These two,
Yeah.
right? Because we're going from something that's acidic to something that's now basic, right? So we've removed all of our plus charges. There's no acidic stuff in our solution now. We just have a bunch of base, right? So you have to remember, you're adding this base makes the whole solution basic, right? So by adding the base, we deprotonate what we can deprotonate in the solution, right? And because we keep deprotonating things, right, we're making the solution more basic inherently, right? So why this massive jump? Because the pK of this happens to be up here at 9.6, right? Does that sort of make sense?
Yes.
Yeah.
So for initially the PKR pretty close to PK1.
Say it again, sorry?
So PKR is pretty close to PK1.
Yeah.
Like close between PKR and PK2.
Yes. Yeah. The distance between, yeah. I mean, like this, so yeah. So these are both acidic pKas, right? This up here is a more basic pKa, right? And so when we deprotonate all of the acid in the solution, right, we're just left with the basic pKa, right?
So a lot of base.
Sorry, yeah, pretty much, yeah. Up here, it's pretty much, I mean, if you're up here, it's pretty much all base, right? Yeah, right.
But if you're in between PK and PK, it's still pretty acidic.
If you're in between these two, like here, yeah, it's still pretty acidic, yeah. Right? Good? Okay. How much time do you have? 6:40. Yeah, gosh.
Is that what you said?
How many more questions do I want to try and get through this because this is a monster of a question. Let's see here. I'll go ahead and do this here because this is the mean question too. Okay, so we have some solution of sodium hydroxide, right, that we can add. We're doing a titration. This is a buffer. The buffer question, right? So we start with 50 molar glutamic acid buffer at pH 2.2. Immediately, my brain is screaming to me, right? Well, pH 2.2 is the first pKa, right, of this amino acid, right? So what does that mean? That means that the amount of base is equal to the amount of acid, right? That's the first thing, right? The second thing is they give us what the equivalence is already. They tell us that we have 50 millimolars of glutamic acid buffer, right? So we have 50 millimolars of glutamic acid buffer. Notice it says glutamic acid buffer. It does not tell you, right, how much of the buffer is acid or base inherently. What it does tell you, because it tells you what the pH of the solution is, right? It has to be equal, right, because we're at the pKa, right? So we split this in half, right? 25 and 25, right? 25 acid, 25 base, right? For the millimolar, right? You don't get it?
Oh, I didn't do that.
You don't have to do it. There's a way you can do this faster with equivalence, right? But I'm just doing the longer way first, right? So with that in mind, right, we just said that this is true, right? Right? So in order to turn, we want to get to pH 9.6 though. That is this up here.
Right.
Right? So in order to turn the remaining acid into base, we add another 25. We add 25 millimoles of OH minus. Right? So now we have 50 millimoles, right? Of this glutamate, right? So we've just added 25, right? We're at glutamate. So we're here now, right? Oh, where are we? We are add 25. Now my brain's shutting down. We've added 25 millimoles of glutamic acid, right? To turn it into not to Not to 4.3 here. Hold on a minute. Why am I not? Yeah, it would be around 3.2 ish. But so yeah, so you've added the 25, right? You're basically at the equivalence point now, right? You're basically I don't just equivalent. There's no really equivalence point here, but like we're around here somewhere, right? Because we've added 25. Now we've gotten rid of all of our acid, right? We only have the base, right? So if we add another half an equivalent, right, we'll end up at the next pKa, right? That's a horrible line. So if we add another 25 NaOH, we'll end up at this next pKa, right? Good? So now we've added 50 millimoles total, right? And then from there, to go from one pKa to the other, right, just add an equivalent, right? So now we just add another 50 millimoles. So now the total we've added is 100 millimoles, right? To get from one pKa to the other, right? So we've gone all the way from the pKa down here to the pKa up here, right? And all you have to do then is do some dimensional analysis, right? 0.1 molar times 5 liters, or 5 mole per liter, right? Fits here, right? Because it's asking you for a liter amount, right? And we're all familiar with dimensional analysis a little bit, how that works. Yeah. Yeah. Yeah, go for it. It's all going to be posted as well on the playlist as well, so. Yeah. Okay. Now, if you're a Chad, you could do this the faster way. um, you so you know the what's it called, the equivalent is 50 millimolar, right? And you know you're at pH 2.2, right? You need to get to yeah, you need yes, yeah. You need to go from 0.5 to 2.5, right? To go from to yes to move from um to move from 0.5 equivalents to 2.5, you need two equivalents, right? One equivalent is 50 millimolar. 2 times 50 is 100, right? That's a lot of information very fast. Does that make sense at all, though?
So yeah, 100 just about
Correct. Yeah, you have to do this, right? Because they give you this solution here, right? In the question. My tip for you guys for doing math on these kinds of weird numbers, right, is turning it into scientific notation, right? So scientific notation makes it a little bit easier. 0.1 is the same thing as saying 1 times 10 to the negative 1, right? And 5 is just 5 times 10 to the 0 power, right? Because 10 to the 0, anything to the 0 power is 1, right? And if you have anything like this, right, like this here, you just move the decimal back by 1 point, right?
also like an example of the calculator do it.
I don't think they do. At least they didn't give it for us. Yeah, so that's what I was saying. Yeah, so that you can do this math in your head. So 1 divided by 5 is just 20%, right? Just be 0.2. And then for doing exponent subtraction, right? If it's division, you just take the powers and subtract them from each other, right? So negative 1 minus 0 is negative 1, right? So you'd end up with 0.2 times 10 to the negative 1. Yeah? No?
Oh well.
If you don't need to do it, don't do it.
Think what you know.
Yeah, yeah. Yeah, yeah, yeah. Yeah, I mean, yeah, that's how I did it for the MCAT, right? So when I was studying for the MCAT, I wrote it like that. Because they give you worse numbers. No. But yeah. Yeah, I kind of messed up this here, though. Let me try and make this look a bit better. That's not what I want to do. I can't make it look good. But does this make any sense at all? Right? If you have other ways of doing this math in your head, don't do this, right? do whatever works for you, right? It just so happens that for me, I like doing it in scientific notation, and I can do that math quicker in my head.
Do you think they would just take 0.1 divided by 5? Oh, obviously
No,
not.
no, because they need a value in liters. Yeah, that's not the unit though. That's 0.1 divided by 5 is not the unit. Like you could if you did that, you'd have to write out the whole entire. You'd have to write out all the units for that, right? So it'd be like 0.1. I don't even know how you do that.
No, just write down the answer as 0. Like,
I know what you're saying, but no, I don't think you can. Yeah, no, you gotta figure it out. Yeah, you gotta do all the math, right? But
so, because I use the charger.
yeah, you're not gonna have to do any more of this math after this test. So yeah, the rest of it is all pathway memorization. So yeah, yeah. Not necessarily, but I mean, it's like bio, right? Where they say it's not cumulative, but it kind of is cumulative, right? Like the knowledge from the previous stuff helps you with the new stuff, right? But yeah, any questions about this? Yeah, this is a stupid question, right? This is a dumb question, right? But hopefully that makes sense. But if you want, you can look at their answer key. Their answer key is also hello. What? Why is it not charging? There we go. Okay. Well, it should be charging now. Now it's significantly brighter. Okay. Anyways, also a devious question,
Yes.
right? Yeah. So they basically just follow up with a bunch of devious questions. Like these are all. This is also kind of mean. Um, yeah, definitely not gonna have time to finish all this in the. Okay, that's fine. Okay, so we'll go over this, right? So for question 3, do I let you guys? Honestly, I might just go over this. Do you guys want time to do it? No. Okay, just go over it. Okay. Yeah, I was gonna say. Okay, so basically here it tells you right that you have some enzyme. I don't care what the enzyme is. Ribonucleic cool, great, have fun. Right? 8 cysteine residues. Okay, they're probably gonna ask me about disulfide bonds, right? So I think you guys have talked about disulfide bonds, right? If you oxidize cysteines together, they make disulfide bonds. If you reduce them, right, they break apart, right? That's something they test on quite a lot. So there's 4 disulfide bonds. Cool, knew that, right? Then they stabilize the protein. Great. So they show me this protein, right? So we have our disulfide bonds. So there's 65 to 72 is 1, 58 to 110, 95 to 40, 84 to 26. Okay, cool. And they're asking about stability. Okay, so if we're looking at stability, right, what you should know about these curves is you're adding some sort of denaturant, right? So in this case, it's whatever the heck that is. I don't know what is that. Guanidine hydrochloride, right? So it's an acid, basically, right? HCl is what you care about there. It's an acid. It's an acidic thing, right? So you're adding this acid, right? And you're looking at how the protein unfolds as you add concentrations of acid, right? So the important things to recognize here are I guess like the quote unquote TM. It's not really the TM. It's like the dissociation point. The point at which the enzyme is half folded and half unfolded is what you care about. That's like the easiest point to figure out, and it tells you the most information, right? So if we look at this, right? So at A, right? It's around here, which is about 2.4, right? So it's right here, right? Just an example of how you go about doing that, right? So you can actually answer the first question technically without doing any math or any kind of matching, right? So it's saying what is this thing 50%, aka what is the amount of concentration required for 50% unfolded, right? So for the least stable sample, the least stable sample just means the one that unfolds the fastest, right? Under the least concentration, right? So it should be just A in this case, right? So it's asking for the concentration, right? And that would be 2.4, right? Because we just looked at that, right? And put the units. For the love of God, put the units, please. They will dock you if you don't put units. This guy did not put units. Please put units. They will remove. It's 2 points, guys. It's 2 points for a reason. 1 point for the answer, another point for the units. So please put the units. Okay. All right. Next, right, we have the percentage for the most stable sample. Um, right. So most stable sample at 4.6 molar. Right. So the most stable sample, right, is going to be the one that has the largest GU HCl 50%, right, and that would be D, right, because 50% here. This is the 50% mark here, right, and so we have to look at the yeah, so it's asking specifically about 4.6. And remember, look at the question. It's asking about folded, not unfolded. The graph tells you unfolded.
Is that the same?
No.
Is that 50% for?
Is it at 50? Right, so this right here is 4.4. 4.6 is here. Yeah, so technically it's up here. So you think it's 0.6. That's unfolded though.
Oh,
They want folded.
40%.
So it's 0.4, yeah, or 40%. Yep. So 40%.
Oh, wait, how do you guys know?
So they're asking for you understand how we get to the most stable sample, right?
Yeah.
That's just D, right? Because it has the highest the HCH, right? It's asking for how much of it will be folded at 4.6.
Right.
So 4.6 is here, right? That's right here.
Yeah.
You would think that it's just 0.6, but that's because the graph is looking at unfolded fraction.
Right.
The question's asking folded.
Yeah.
So the other 40% must be folded.
Oh.
He's had enough already. Right? Does that make sense how what we're doing here? Right? Okay. This one this is the weird one now, right? So now we have to assign value, like I'm just gonna this honestly, but okay. But right. So for part C, right? We have to look at these, right? And if you have to leave, by the way, at 7, it's fine. I'm not gonna cry. Huh? Hey, yo, let's go. Okay. Okay. What exams next Friday, right? Yeah. Okay. Okay. For this question, right? Down here, right? It says to identify samples corresponding to each curve. This can be. I think this question probably took me the most time, other than this, right? What do you mean? Score? I got a 86. I missed these two 4-point questions. Yeah, for really dumb reasons. Right, so it would have been a 94 if I had.
Oh, this is your test?
Yeah, this is my test. Yeah. I took this test. Yeah, this is my exam.
So hard.
Yeah. I know it was a pain. Yeah. I don't remember what the average was. Yeah. So
Why was it a pain?
it's like Robinson's Chemical Mysteries, but it's a protein mystery. Yeah, that's the thing. You get one for every exam. Not actually. You get one for this exam. This is the only exam they can really do this on, right? The other exams is like pathways, so they can't really do this. But all right, let's move up here, right, to this, right? So this is just like a panic fest. Like, how do you even tackle this, right? Right, that disulfide bonds naturally make things more stable, right? So if I remove a disulfide bond, the thing just dies, right? So if I removed this disulfide bond, it'd be sad, right? If I removed this disulfide bond, it'd be sad. If I removed two disulfide bonds, it would be even more sad, right? That makes sense, right? Remove bond equals sad, right? So you should be able to say, if I just have a wild type ribonuclease with no problems for it, that should be pretty damn stable, right? That's probably going to be the most stable. That's probably going to be A, right? Huh? Sorry, D. D is the most stable. You got me there. Yeah, D is the most stable, right? So D is the most stable. Yeah. So sample one is probably D, right? Does that make sense? How we got there, right? The KD 50 for the GU HCl 50, right? For D is super high, right? It's the highest of all of them, right? Which means that it takes a lot of stuff to actually unfold the thing, right? And that makes sense because all of our disulfide bonds are actually intact, right? So that makes sense, right? Okay. For sample number two, we have this thing in the presence of a reducing agent. Okay, if I have a reducing agent in there, everything dies, right? So all these disulfide bonds are gone, right? That's basically just an unfolded protein, right? So that is ridiculously unstable, right? So that's just going to be A, right? And that makes, do we understand why that is the case? Okay. So 2 would just be A. Okay. Okay, these three are where it can get a little bit weird, right? So, ribonuclease with cysteine to alanine mutation. So, cysteine, right, is what does our disulfide bonding. If we replace that with an alanine, which does jack all, right, alanine doesn't do anything, right, you've basically lost the function of that amino acid, right? So cysteine is no longer there. If one cysteine is gone, you can't form a disulfide bond, right, because this is just not there anymore, right? So we've essentially just reduced that bond, right? It basically seems like we reduced it, right? So, oh my god, wait. So this bond, right, is gone, right? This bond right here is not there anymore, right? You would agree that that is pretty unstable, but it's not as unstable as if you just put the whole thing in a bunch of reducing agent, right? Because we've only reduced one of the bonds, not all of them, right? So, by that logic, it should be between A and D. So it should be B or C, right? But I don't really know, like, compared to these other two. If I had to guess, I'd probably say C right now. But let's go over the other two before we make any judgments, right? So if we look at, oh my god, if we look at this one, ribonuclease with C58 and C110 alanine mutations. Okay, where's C58 and where's C110? 58 is here, 110 is here. So they're both part of the same disulfide bond. So that's not any different from if I just mutate cysteine 58, right? Because they're both taking part in the same disulfide bond. So if I mess up one, the disulfide bond doesn't form. If I mess up both of them, it doesn't form, right, either. So it doesn't matter, right? So those are actually both the same, right?
Would get hydrophobic.
It could, but in this case, the stability of the disulfide bond is completely lost. You don't have the disulfide bond anymore, right? And the disulfide bond is one of the most important bonds for stability, right? Hydrophobic interaction is very important, right, for general folding of a protein, right? But in this case, the question is specifically talking about these disulfide bonds with respect to how they stabilize the protein. So, right? So because of that, I can say that if I mutate 58 and I mutate 110, it's going to be the same as if I just mutate 58.
In order software.
Yes, because one is covalent and one is not, right? Disulfide bonds are covalent bonds, right? And
We were told that hydrophobic interactions are the biggest drive for problems to fold.
correct, yeah, they are.
Doesn't the entropy
Ye-
with water
Yes,
increasing?
yeah, yes, because the entropy of water increases, it's favorable to put the hydrophobic things on the inside of a protein, right? Yes, that is true, right? The thing is with this question is specifically talking about the disulfide bonds, right? It is talking about that these things help to stabilize the native fold, right? So like you're right that hydrophobic interactions would play a huge role in the folding, right? But the disulfide bonds play a really big role in actually helping it fold in the first place, right? Or like helping it fold and then like locking it in place, right? So Does that kind of answer your question? Yeah. Okay. So like you're right, right? The hydrophobic interaction is what drives protein folding, but
I really like question.
uh-huh.
I was thinking that if we were to replace C58
Mm-hmm.
and C110 with alanine,
Mm-hmm.
that we could just replace that with hydrophobic interaction.
Yeah, but alanine's really small, right? So if you had maybe argued like tryptophan, maybe I could see that, right? But because alanine is so small, it doesn't really interact with anything, right? So like if you're gonna propose the hydrophobic argument, use like phenylalanine or tryptophan or something like that, right? Yeah, yeah. I think the other thing to note here is that alanine is one of the most common like loss of function mutations we make in just science in general, right? So like if you ever see like a serine to alanine, cysteine to alanine, whatever to alanine, right? Assume what they're doing there is removing the function of the protein previously, like the previous function of the protein, right? Because what they're trying to do there is lower the function of the actual protein without just messing up the structure completely, right? They want to see what happens if you remove that amino acid. Does it actually affect the function of the protein, right?
We just replace the amino acid with alanine, we really affect the structure.
It might,
Other changes.
right. It might affect the structure, but the hope is that it doesn't affect the structure enough where it just destroys everything, right? And actually, if it does destroy everything, then you know that that amino acid is integral for the protein, right? So either way, it's a win-win, right? The point is that you mutate to see if it's important, and if it degrades everything, you know it's important, right? So, does that make sense? Good? Yeah? Okay. So we based off that, right, we can say that 3 and 4 are equal, right, in stability, right? Yeah? Okay. Does that make sense?
Yeah.
Yeah? Okay. You're right, Leon, that hydrophobic interactions are important.
No, or they will collaborate over like one more stable compared to this
Uh, why?
this other open to make folded unfolding a lot more. Like
Yeah, but remember what I said that alanine's not really something that's going to hydrophobically. Yeah, it's pretty dang small. Yeah, if you had said also just remember in general, right? Covalent bond. Just remember chemistry, right? Covalent bonds are the strongest bond, right? Everything else is weaker. Hydrogen bonds are weaker. Hydrophobic, like van der Waals forces are weaker, right? They're all weaker, right? A covalent bond is very strong, right? It's very rare in nature, right? That's it's ridiculously strong, right? So that's why we classify covalent bonds separately from all our intermolecular forces, right? So if you see a covalent bond and it's been disrupted, just think that's really unstable. Like imagine if you take a peptide chain, just chop it in half, right? The protein's not going to work, right? So that's a covalent bond, right? You broke the covalent bond, right? The protein doesn't work anymore, right? For the case of folding, yes. For folding, it does matter.
yeah.
Folding, the whole point of that is to make sure that all of our hydrophobic interactions and all of our hydrophobic amino acids are inside. But you can't do any hydrophobic folding if you cleave the bonds that actually make it possible to fold in the first place, right? So if I cleave all of my covalent bonds that are holding my protein together, I can't fold it. I just can't fold, right? Yeah. Okay. So if we look at 5, right? 5 is saying that you mutate cysteine 58 and cysteine 40. So cysteine 58 is here again. I don't know why I removed that, and cysteine 40 is here. So now we're messing with 2 disulfide bonds instead of just one, right? So that's unstable, and not as unstable as if you just dump it into a bunch of reducing agent, right? But it's definitely less stable than if you just mutate one of the alanines, like we did in this first one, and it's definitely less stable than if we mutate both of the cysteines on the same disulfide bond, right? So for that reason, right, we can say that 3 and 4 are more stable than 5, right? Does that make sense? Right? So if we're looking at these curves, right, I would say that 3 and 4 are both, like, you can assign C to both of them because they don't give you another option, right? So I'd probably go with this, right? And then for 5, I would just go with B, right? Good? Cool. Yeah, moving on, right? Okay. For part D, this is an interesting question, right? So if you want to perform a refolding experiment, right, it contains this. Okay, you want to generate the native fold, right? In what order do you remove things, right? So let's think about this, right? And I actually have to think about this a little bit too. So like if you remove so right now as it is, right, the protein is both denatured and reduced, right? Basically it's screwed, right? So if we remove the reducing agent first, right, we will oxidize everything in its denatured form, right? So that means all the disulfide bonds that are not supposed to connect with each other will start forming, right? So basically the protein's still screwed, right? If I remove the GuHCl, the guanidinium chloride first, right, the protein can start refolding, right? And then if I remove the reducing agent, right, now the protein is folded correctly, and now the disulfide bonds are actually the correct disulfide bonds that should be forming, right? The cysteines are actually in line, right? The correct cysteines are in line, right? Does that make sense? Okay, I won't write all of that because I think you guys that makes sense to you guys, right?
I was wondering, in your lectures,
Hmm.
they tell you that, like, researchers usually, like, heat up in nature. No. Each time,
Yeah.
yeah.
Yeah. I'm gonna be honest with you. The whole yeah. I mean, they might have talked about it briefly, but like, no, not really. So yeah, same thing with this question, right? Like, we had like, if I didn't do the practice exams, I would have had no idea we were doing SDS page stuff, right? I would have been screwed, right? So yeah, but that makes sense, right? We're good with part D here, right? Okay, more math. Okay, so you guys, I don't, have you guys done the binding stuff yet? Ligand binding stuff yet? I think that's Friday.
Like, what do you mean?
Like ligands binding to proteins. So like, no, yeah, that's Friday for you guys.
I want to know what's happening before.
Huh? I mean, it's probably gonna be Thursday night because I have an exam on Thursday, and you guys have your test on Friday. Yeah, I mean, yeah, we'll see. I'll ask. I mean, if you guys want it, sure, I can do it, but I'm not gonna. If I don't need, if you guys are going to be studying that night, it's probably better if you guys study alone than like go to a review session, right? If that makes sense, right? Up to you though. I mean, I'll probably put out a poll or something, right? If you guys want to, I can do it. But yeah. Do you guys want to go over this? I don't. If you guys haven't really learned it, yeah. Let me just give you like really quickly like what's going on here. There's a formula here that you can use, right? Basically, and this will all make sense when you actually see it. But like, you're going to use this formula. Concentration of ligand is equal to the KD plus concentration of ligand again. Um, and basically, you're going to substitute some numbers from this graph into this, and you'll get some number, right? The other thing that's important to know is cooperativity. If a curve looks sigmoidal like this one in B, means that the binding of one thing affects the binding of another thing, right? So if I bind one thing, another thing will the affinity for the another thing will also be changed, right? If it's hyperbolic like this, right, there is no such cooperativity. It's one binding site and there's nothing else, right? But so basically, what you can say from that is that C and A are not cooperative, and B is a cooperative binding thing, right? Because yeah, so the binding of one thing affects the binding of another thing, right? And that's what the bottom question is asking, right? Explain the difference between the two curves, right? You can say that one has one binding site, so B and A have one binding site. C and A have one binding site. B has multiple binding sites, and for C, the binding of one thing doesn't affect the binding of another, and for B, the binding of one thing does affect the binding of another thing. But hopefully that makes more sense when you actually get to it. But yeah, that's all in the answer key for you as well. Like they do list very nicely how the points work. So I'm actually gonna skip down to these questions first. These are actually really really dang fast. Um, for
Can we do the overall question?
do you want to do them on your own right now? Yeah, sure. If you do want, if yeah, go for it. If you want to do them on your own for 2 minutes, yeah, that's fine. Go for it. It should not take you. Well, actually, don't do B. I don't think you guys can do B. You can do C though, right? No, you can't. Just do A. Just do A. Realizing that those things are both technically hemoglobin related. If you remember stuff from BIOC 20, you might be able to do C, but I won't make you guys do that. Yeah, it's the whole. Do you remember the hemoglobin curve from 220? The oxygen curve, the O2 curve.
Oh, yeah.
Yeah, yeah. It's this thing, right? So
Yeah. It's really the last.
50% here. It's like occupancy.
Oh,
Yeah, it's like a 220, and like you have different different PO2s, like millimeters of mercury here.
wouldn't the buffer section?
No, because this has to do with oxygen partial pressure,
Uh,
not with not with buffers. Yeah. All right, so we're good with A, right? I go over it real quick. Um, so if you metabolically active tissue requires, I sure hope more O2, right? And it also generates increased amounts of this, right? Because of the fact that we do that whole the whole not heterostomer, right? Yep, the CO2 plus H2O makes bicarbonate H plus, right? Increased CO2 shifts to the right. Yep, good. Okay, cool, done. Okay, I want to do this question because this question I feel like I don't know. I have an inkling that they will do something like this on a test, right? Or at least have something to do with column chromatography, because you guys had a whole lecture on experimental techniques, which is crazy, right? So, yeah. So you discovered a protein, right? Cool. I don't care about what this protein does, right? I just want to be done with this test. Okay. So it's cleaning toxic spills, so it binds mercury and it binds cadmium. Okay, cool. Right. That's what I get from that. You do some experiments. You do an ion exchange slash exclusion and exclusion chromatography, right? So this is the important part. The native protein binds to the cation exchange at pH 8, right? So what does that mean? Yeah, sorry, do you want to say something? Or the protein is positively charged at pH 8, right? Because remember, with cation exchange, we're exchanging the cation. Beads are negative, right? So if we exchange the cation, right, and we put this protein in, it must be positively charged. Does that make sense?
charge protein.
Right, because the beads are negative, right? The beads are negative. Cation exchange. Exchange the cation, right? So we're changing out this placeholder cation for the protein that we're putting in, right? Good? Okay, so the protein's basic, right? So based off of that, I can tell you that the PI is above 7, right? Because if it's a basic protein, right, it must have a bunch of like arginines and lysines and stuff, right? And their PIs are like in the 9, but they're higher, right? So we must have a high PI, right? A PI higher than 7, right? So if they ask a question about PI, I know what the answer is, right? Good? Okay. After performing a size exclusion chromatography, the native protein flows straight through. That's a typo. Okay. Flows straight through the size exclusion column K containing resin that separates proteins in molecular weight. Okay, blah 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 blah. So it flows straight through it, which means that if it doesn't get right, flow straight through it. Yeah, flow straight through it. Yeah, so it doesn't get caught in this, right? So it just goes straight through, which means it's not any of those sizes. So it's not between 10 to 80 kilodaltons, right? Because if it was one of those sizes, it would get stuck in those. It would get stuck in the column, right? No? Yeah?
Flow straight through there.
Yeah.
I mean, it's in the range. Because O is the bigger.
It's too big. Yes. Yeah. It's too big. Yeah.
That's good. Flow through the resin or flow through the style?
It would. Oh no. So it wouldn't flow through. It wouldn't. It would flow through the sides, right? Because if you want it to get stuck in the. No, do you want? Yeah. If you want it to get stuck in the. Right.
Say flow straight through a five column containing resin.
Yeah. That separates proteins and like right. So the resin itself separates proteins in this range,
Right.
but it's not. It's flowing straight through that, right? So it's not separating them, right?
So I'm saying it's
So if it was in that range, it would get stuck in the resin beads, right?
but it's saying it's in the next like 35 minutes.
Sorry, what?
So it's saying it's in the next range.
Yes, right. So the protein is separated on a side exclusion chromatography containing resins of 30 to 100 kilodaltons, right? So it's between 80 and 100, right? Good, yeah, right. Then you do an SDS page, and you observe that one major band with okay. This why is there one major band?
Was that this picture?
What is SDS page?
It's like I always says that.
It is gel electrophoresis, right?
One band. One protein or like polymers 30 kilodaltons. So it has to be multiple of those.
Right. Okay. So you know that your weight's between 80 and 100, and you know it has to be a multiple of 30. There's only one option here, right? What's the mass?
Subunit?
So it's subunited, right? Yeah.
90.
It's 90 kilodaltons for the whole thing, right? Right?
Whoa.
Does that make sense? And remember what SDS page does, right?
Where's the subunit, brother?
SDS page denatures the subunits, right? They didn't say reducing conditions, right? So it's not from disulfide bonds, but it's separated based off of other interactions, right? Right? Does that make sense?
What?
Yeah, yeah, man. Yeah, they're a bit mean. So, right? Does that make sense, guys? Yeah, this is a hard question, right? Right. So you can tell me now, right, that it has to be between 80 to 100, right? That's not an 8.
I'm kind of already it's not within 8, but it's within 30 dollars. So you want less than 100. Okay.
Yeah. So right. So you can so right. If it's 10 to 80, right, like you said, right, it can't be 30 to 80, right, because it fell through there, right? Right. So it has to be from 80 to 100.
So it didn't work from 10 to 80.
It didn't work from 10 to 80.
Oh,
Right.
it worked.
Correct.
So that means okay. So
Right. Because it didn't work from 10 to 80, right? If it did work from 10 to 80, then it should also work. It would also work from 30 to 100, right? Right. So, but because
flowing straight through means that it didn't flow through the resin.
it didn't flow through the resin, yeah.
Okay.
Yeah. 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 They're tough, man. They're not easy, right? Does that make sense though? Yeah. So I mean, you guys haven't really done, but basically, right, what this is saying, right, is that as you increase the concentration of mercury, right, the binding of this becomes cooperative, right? So the binding of more mercury changes the affinity for more mercury, right? It also tells you that it's affected by cadmium. So if you have 0 cadmium, right, it's not very cooperative, right? But if you add more cadmium, it's very cooperative, right? It becomes more cooperative, right, as you add more cadmium, right? That's what that graph is saying. But yeah, so we'll do A. A should be relatively fast. So you lower the pH of the native protein. What? You Okay, yeah, so right. So you have a solution of the protein, right? You lower it to 6, right? Circle the choices within the parentheses to complete the most accurate statement. Okay, cool, right? So at pH 6, right? So this is about the charge, right? So the charge was discussed up here, right? We said at pH 8 it is positive, right? So if that's pH 6, it's also positive because it's lower, right? We're at a lower pH, right? So it still must be positive, right? So at pH 8, right? It's a positive protein, right? If we make the solution more acidic, right, it should still be positive, right? Think about like if I have lysine, right? So lysine, the amino acid, right? Lysine at pH 8 is positive. Lysine at pH 6 is still positive, right? So it should be soluble, right? Because it's positively charged, right? Well, I don't know when it would ever precipitate. I'm not gonna lie. When I think like if you have a Zwitter ion, it would precipitate. But that's the only thing I can think of. Precipitate? Yeah, when it's a Zwitter ion. Yeah. For what? We don't. No, it wouldn't be. If it was negative, it'd still be soluble, though, right? It has to be neutral because water is polar, right? So if it's negative, it would still be soluble in water. Basically if it has a charge, it's soluble in water. Well, it's in water though, right? We're always in a solution of water, right? Okay. You guys actually already solved part B. Is it a monomer or is it a multiple subunit? You said it's a ligamer, right? You said it's 330s, right? So you got that, right? What? You said a ligamer. So yeah, so it's a ligamer, right? Because we just said it's 3 things of 30, right? What's the molecular weight of the native protein? It's 90, right? With 30 subunit, 30 subunits. With 30 kilodalton subunits, right? Briefly explain your answer. I don't care. Briefly explain your answer, right? You can go ahead and talk about how because it didn't elute through the 10 to 80, but it did go through did separate in the 30 to 100. You know it has to be between 80 to 100. And because you know that the SDS page only showed one band of 30, right? It must be that the protein's total weight is 90 with subunits of 30, right? That's like a basic way of explaining it, right? And for D and E, it's all about cooperativity, right? Um, for cooperativity here, good question. Yeah, go for it. The 3 bands on where is it? Oh, this? No, so yeah, so this is where it was. So yeah, this is why it's a bit weird. So this is one protein, right? But those subunits could interact in different ways, right? So like for example, if I have my 3 subunits and I bind like, let's just do this, right? Let's just have these be my subunits, right? Let's say that I bind a mercury like right here, right? That might change the shape of the enzyme, so the enzyme actually might like bend in on itself or something, right? And it might reveal like another binding site. So it might, oh God. So it might like do something like this. It's gonna change the shape, right? And so you might reveal another binding site in like this pocket here or something, right? Just think about it like that. That's what cooperativity is, right? It's when binding of one thing alters the structure of the enzyme, and so now another thing can bind in the spot that's been released, right? That's why these curves look like this, right? Huh? I did not know. These are cooperativity questions. Do you guys want me to do this? Huh? Yeah, we have like 1 minute. So, do you want me to do these? Yeah? Yeah, you can leave. Yeah, you haven't learned it. That's the thing. Yeah. I mean, like, yeah, that's the thing. So, you won't learn it until Friday. But, yeah. Okay, that's fine. You can leave if you want. Yeah, I'll be here for, I mean, yeah, I'll be here till we close anyways. So, do you guys want me to do, okay, I got the survey. It was 50-50. It was literally 50-50 for doing the quiz stuff. Oh, okay, this guy. Okay, okay, let's just do you guys want me to do the quizzes or do you guys want me to do lecture reviews?
What was it? Should we do both? Like balance both? Oh, the opposite?
Yeah.
Um, that's sure. I mean,
Yeah, what? I'm not doing that. I'm sorry, bro.
that's right now. Yeah, we do have a question. Yeah.
Oh my god. Oh no. That's horrible.
No, man, it goes to what you're saying. Oh, the first session, mine is on first thing. Yeah. So, yeah, because there's hour. And so it's not in five. It's on Thursday, but. Oh, really?
Rest in peace, dude. That's so rare.
Okay, we used to Peter and stuff.
Okay. Yeah. I honestly, what I might do, I could upload this. I'm thinking about not uploading this and re-recording it, though. Do you guys want me to upload this?
Uh, like the video?
Yeah, I might re-record it. Okay, okay, I'll upload it. Yeah, I'm not gonna bother with these. If people have questions about these, I mean, just you can just ask, right?
Yeah.
But it's friggin' 7:30. So
Appreciate you.
yeah, no worries. Yeah.